yk and yk minus 1. And that's why we can't express this yet as a typical non-stationary iterative method. So that's why we can't express xk easily in terms of xk minus 1. So by changing from this linear combination to this one, and having each of the w's satisfy this, we're going to set ourselves up for an efficiency gain. Now, here's where we use the fact that, okay, so I have LK, DK, WK is equal to E1. Now I'm going to break the system up into blocks because LK can be written this way. I have LK minus 1 occupying the upper left K minus 1 by K minus 1 block. Up here, I have 0 because LK is a unit lower triangular matrix. Over here, I have 1. And then in this space, I have all zeros, except at the very end, I have little l k minus 1. So this is the structure of LK defined recursively in terms of LK minus 1. And then, similar thing for DK. I give it the same block structure. So I have DK minus 1 up here. I have little dk down here. Everywhere else I have 0. And then I have now this is WK. I have the component WK down here, and I don't know what I have in here just yet, so I'm just going to call this Z. I got to figure out what that is. And this is equal to E1, but E1 is just E1 in a lower dimensional space, and then the last component of that is 0. So I'm seeing what is the relationship between case k minus 1 and iteration k. So now what I'll do is I'll multiply all this out and see what I get. So I have LK minus 1, DK minus 1. So multiplying these out, plus 0 times 0, so I get nothing there, times, actually, I'll carry out the matrices first. Alright, and then I have LK minus 1 times 0, 0, so I get 0 over here. And then I have 0, so this row vector times this matrix is going to be just, that's going to give me another row vector. So I get 0, 0, LK minus 1, DK minus 1. So that's what I get from multiplying this with this. And then, so I'm just doing like matrix multiplication only with blocks. Plus this times this, which is just going to give me 0. And then for this spot, I get 0, and then I have dk down here. And then I have z little wk equals E1, 0. So now I can multiply this out and get a decomposed system of equations. So I have LK minus 1, DK minus 1 times Z plus nothing equals E1. And then down here I have all zeros times LK minus 1, DK minus 1, ZK minus 1. So this is a dot product. Plus DK WK is equal to 0. Now, here's a system that WK satisfies. Notice this is exactly the same system except it's K minus 1. Therefore, z is actually the vector wk minus 1. So I can fill that in here. So that means that each wk depends easily on the previous one. These first k minus 1 components never change. We just add on a new one. So in fact, I can fill that in here. Okay, so in other words, by changing the linear combination that's used to express my x's, I have the vector wk is just the vector wk minus 1 with one element, one entry wk tacked on to the end. And that happens to satisfy this equation. Okay. All right. Now we use the fact that xk minus 1 is equal to p tilde k minus 1 times wk minus 1. And xk is equal to pk tilde wk. But pk tilde, we're growing columns again. So the first k minus 1 columns of this matrix right here, we're just adding on a new column. So if I put these two relationships together, I can write this as pk tilde minus 1, or p tilde k minus 1, vector pk tilde times vector wk minus 1, element wk. Well, that would be pk minus 1 tilde, vector wk minus 1, plus vector pk tilde wk. And this term right here, the first term, is just xk minus 1 plus pk tilde wk. So now, summarizing all this, I now have a simple relationship between, oops, that should be x parentheses k, between xk and xk minus 1. I now have the makings of a non-stationary iterative method right here. So that's what I was after. So these vectors, the pk tildes right here, you can think of these as search directions. So if we have an easy way of getting those, then we're really in business. Because the whole challenge in a non-stationary iterative method is, first, what are the search directions, and then what do you multiply them by? Once we have that, then we're good to go. So we just got to figure out how to quickly compute these, and then we have our conjugate gradient method. Okay. But there's one other very important thing about this matrix, this pk tilde, that is very helpful to us, that gives us an effective iteration if we keep in mind how it was defined. Now, if I look at matrix pk tilde transpose A pk tilde, but now I need to use how pk tilde is defined. Well, that would be qk lk inverse transpose A qk lk inverse transpose. Okay. That's the definition of pk tilde. Now, if I work this out. Remember, a transpose of a product is a product of a transposes in reverse order. So this is going to be LK inverse, QK transpose, A, QK, LK inverse transpose. But QK transpose AQK, that was defined back on Monday to be TK. But TK has a LD-LT factorization. So we'll fill that in. That's LK, DK, LK transpose, LK inverse transpose. Okay. And wow, look at all that cancellation. So these cancel, and these cancel because they're all inverses of each other. And what's left is DK, which is a diagonal matrix. So, what does this really mean? That means that if I look at if I define the matrix PK tilde to be vectors, P1 tilde, P2 tilde up to PK tilde, so these are my search directions, then suppose I is not equal to J, and I look at the vector Pi tilde transpose A Pj tilde. Well, these are the ith and jth columns of a matrix Pk tilde. So that would be Pi transpose A Pk tilde Ej. So that's going to be Ei transpose Pk tilde transpose A Pk tilde Ej. But this matrix in the middle I just showed was dk. So it's Ei transpose dk Ej. But dk is a diagonal matrix. This is an off-diagonal element of a diagonal matrix. Has to be 0. So, excuse me, so what that means is the search directions the vectors P1 tilde, P2 tilde, and so on, they are not orthogonal, they are said to be a-orthogonal. Because if you had Pi transpose Pj equals 0, that would be orthogonal. But there's an A in the middle, so we say they're a-orthogonal, or another term for it is A-conjugate. So this is, we've seen the first part of how the conjugate gradient method gets its name, that the search directions are all conjugate. So they're not really orthogonal, but they're at least orthogonal in a certain sense. In other words, all the directions have this notion of linear independence that's quite strong because it's just a twisted form of orthogonality. So in other words, this iterative method, unlike steepest descent, is actually going to have some memory. It's not going to cover old ground again. What am I doing with this? Those aren't my notes. Okay. All right. Now, okay. So one other thing is, from the definition of the pk tilde, so we have this relationship that qk equals pk tilde lk transpose. Well, lk is a unit lower triangular matrix that's now been transposed here. So if I look at this equation column by column, okay, actually, I want to write it this way. Okay, so I have P1 tilde, P2 tilde, PK tilde, search directions. And then my matrix is 1s on the diagonal. And then I have my off-diagonal entries, L1, L2, up to LK minus 1, equals the columns of this matrix, which is Q1, Q2, up to QK. Now, if I multiply this out, and I look at column, a particular column of this, matched against the same column of the left side, here's what I'm going to get. So in fact, I'll just go ahead and take the last column. So QK on the right side equals, on the left side, I'm going to have this last column times these columns here. So it's going to give me PK tilde plus LK minus 1, PK minus 1 tilde. Okay. So now we have a simple relationship between the normalized residuals for the Lanczos method and the search directions. And we're going to use this to get ourselves a simple way to actually compute the search directions. Also, by looking at first columns, I have P1 tilde is the same as Q1. And this is known from Lanczos algorithm. Q1, in fact, is just B divided by its 2 norm. So at least our initial search direction is known. And as we compute the Qs, we can use that to get all the other search directions. But the thing is, we would like to get the search directions directly. We don't want to have to bother to compute these Qs at all, if we can help it. Okay. So in order to get a better way to compute these search directions, we can use this condition here, that they have to be A orthogonal or A conjugate. So, all right. So what I'm going to do is, so to get the search directions more efficiently, I'm going to define the actual search directions we'll use, because I have these P tildes all over the place. Those are not the true search directions we're going to use. They're just parallel to them. So I'm going to let PK equal 2 norm residual RK times PK tilde. So it's a sort of normalization, but it's not true normalization. But this is going to be more convenient for us because now I can use this up here to get this kind of relationship between the search directions and the residuals. So now what I'm going to get is each search direction, PK, is equal to, because if I multiply QK, I'm going to multiply through this equation by the norm of RK squared. This is a unit vector. So this effectively is going to become RK. So PK is equal to RK plus some unknown constant, which I'll call mu k, times the previous search direction. So this is the relationship I'll actually use to get each search direction from a previous iteration, because what I'm saying is each search direction is equal to RK, which is the steepest descent direction, plus some multiple of a previous search direction. This is why the method is called, the method you still haven't seen yet, but hopefully will by the end of class today. It's called the conjugate gradient method. Its conjugate comes from the fact that the search directions are A conjugate. It's conjugate gradient because each conjugate search direction is obtained from the gradient, or minus the gradient really. But we have this extra term here that kind of fixes this search direction, because just using RK, that's the steepest descent method. We saw that doesn't work very well. So this correction using other conjugate directions will give us the speed up and convergence that we're looking for. So now the next challenge is, how do we get this constant? Because if we have a good way to do that, then we're pretty much there. Now, so the given parameter is mu k. What we use, in fact, in the search directions are A conjugate. Pk minus 1 transpose APK has to equal 0. So now what I'll do is I have Pk is equal to Rk plus mu k Pk minus 1. So I'm going to multiply both sides of this equation by A and then by Pk minus 1 transpose. So I have Pk minus 1 transpose APK is equal to Pk minus 1 transpose ARK plus mu k is the constant, I'll pull it out. Pk minus 1 transpose APK minus 1. Now, the search directions are A orthogonal, so this left side is 0. So now I can just solve this for mu k. So mu k is equal to minus Pk minus 1 transpose ARK over Pk minus 1 transpose APK minus 1. And this denominator will never be 0 because A is symmetric positive definite. Therefore, the denominator will always be positive. And the search direction is not going to be 0. If we did have a 0 search direction, we'd stop. Okay. So, the nice thing is, now that we have a value for mu k, the benefit of that is there's no longer any need to compute these normalized residuals, these QKs. We can forget about those. We'll just use the residuals, because we know how to compute those. Once we have a solution xk, Rk is B minus AXK, so that's no problem. But it turns out we need to make this algorithm even more efficient, because notice what we have here is, okay, so actually, well, this could be done just using a single matrix vector product. But the thing is, we want to make sure to use as few distinct matrix vector products as possible. And it turns out certain relationships that we have in this algorithm that I'm putting together slowly and painfully piece by piece. We want to make all these as efficient as possible. Okay, now, if we take a look at the residuals, so Rk plus 1 is equal to B minus AXK. But now I'll fill in what xk is. So that's B minus A. xk is xk minus 1 plus wk pk tilde. But B minus A xk minus 1, that's the same as Rk. So Rk plus 1 is equal to Rk minus wka pk tilde. So now we have a simple relationship between each residual and a previous one. Now, all the residuals, however, are constructed so as to be orthogonal. So now I can take the dot product of both sides of this equation with Rk. So I'll have Rk transpose Rk plus 1, which is 0, is equal to Rk transpose Rk minus Wk Rk transpose APK tilde. Okay. Because all of this is 0, that means I can express Rk transpose Rk as oh God, I thought I corrected this mistake in my notes. It's going to take me off if I didn't. Oh, wait a minute. fine. WK RK transpose A PK tilde. Okay, so this is one relationship depending on what you need. But what I could also do is I can go back to this equation. I'll fill in the left side again, RK plus 1. I took a dot product of both sides of this with RK. I can also take a dot product of both sides with RK plus 1. So I have RK plus 1 transpose RK plus 1 equals RK plus 1 transpose RK, which is 0, minus WK RK plus 1 transpose A PK tilde. So now I can have this is equal to this term here, minus WK, etc. So if I take all the indices in this equation and let's see, and shift them down by 1, then I have RK transpose RK is equal to minus WK minus 1 RK transpose A P tilde K minus 1. Okay. So now I have these two relationships, but then what I'm going to do is I'm going to take this one right here, and I'm going to shift the indices in that one too. So wherever I see K, I'll replace by K minus 1. Okay. And the reason I'm going to do that is, now if I divide these, I can get the WK minus 1s to cancel out. Okay. Now,